So I had given a problem, for practice. So I thought I will just, continue with that. I hope all of you have solved it. Okay. And it's just a standard application of the formulas, right? So we are considering or we need to calculate XC1, okay, XC2. So two conditions are taken. And based on that, we are calculating the capacitances, right? So, yeah. So we have the formula here, okay, 1 by 2 pi F1 and into R1 by 10. So we have taken this since, the resistance, we are actually taking a smaller resistance and a larger. So I think by now you should be knowing that resistance and capacitance are, inversely proportional. Okay, meaning if I am taking a lower valued resistance, then it means I need to match it up with a higher value capacitance, right? So having this in mind, we have framed, or we have looked into this formula and we have derived, right? So accordingly, we have got about 1.18 and 0.42. So have you all got this values, 1.18 and 0.42 microfarad? Yes. Yeah, have you all got it?
Yes, sir.
This was actually, given for the practice. Okay. Fine. So for today, we'll be looking into high input impedance capacitor coupled voltage follower. Now we had just looked into the capacitor coupled voltage follower, but then the differentiating factor here is going to be high input impedance. Okay. Now, how is this important? This high input impedance is what we will be looking into in detail. We'll also solve a problem based on this concept, right? And we'll also look into computer analysis as to how this can be designed using computer and what results are thrown up on the CAD tool, right? So we are looking at a very high input impedance, right? So that's the property of an op-amp, as we have been learning so far, and very low output impedance. So here, if you can recall, right, we have the input coupling capacitor and the output coupling capacitor. But the extra thing that we are doing here is we are adding another capacitance called C2, right? So we will just look into it and we will see, what exactly that, we are going to derive and how we are going to take this forward. So the input impedance of capacitor coupled voltage follower discussed previously is set by the value of resistor R1, right? So let me probably take you there and just to the normal voltage follower. Yeah. So, this is what I was talking to you about. Okay, so we are just looking at this circuit here. Okay, the capacitor coupled voltage follower. So you can see that, we do not have, a capacitor here, nor we do not have an extra resistance here. So those are the things, which are added up when we talk about high input impedance. Okay. Fine, we will move forward. So keeping that circuit as a reference, okay, now we'll be dealing only with high input impedance, which is Z in. Okay. So this value of the resistor is actually, it was decided by R1. Okay. So this gives a much smaller input impedance than that of direct coupled voltage follower. So we are looking at, building up the input impedance. What can I make to make this input impedance very large. Okay, so that is what is our goal as designers or engineers. So here you can see this figure. Okay, so it shows a method in which the input impedance of the capacitor coupled voltage follower. Now keep in mind, whenever there's a word called capacitor coupled, it means you should actually concentrate on these capacitors here. Okay, so whenever there is capacitor coupled, it means input is capacitor coupled and output is also capacitor coupled. But the extra thing, as I mentioned, the extra thing that we are looking here is at this capacitor and at this resistance here. Okay, fine. So we are making this combination so as to make our input impedance very high. So if I have to compare this circuit along with the normal capacitor coupled voltage follower, the input impedance there would be much lower, okay, compared to this configuration. So we will see how it works. Right. So capacitor C2, okay, so we'll be concentrating on this capacitor. In figure, couples the circuit output voltage to the junction of resistors R1 and R2. So you have a junction here which is made up of two resistors, and these resistors are called R1 and R2. Right. So I am actually looking into putting. So we are concentrating at this junction, and we are also looking at capacitor C2, and we are concentrating on R1 and R2. Right. C2 behaves as an AC short circuit so that V0 is developed across R2. That is very important, right? Whenever we have a resistor, the main reason that we utilize it is to make sure that there is some kind of current that gets generated, and due to which there can be a voltage or a potential difference. So what we can understand here is the importance of C2. So C2 behaves as AC short circuit, and because it works as a short circuit, because see, there is a charging and discharging happening, right? So there's a connection there, right? So at one point of time it charges and then discharges. So we have a combination here of C2, okay, the capacitor C2 and R2. These are the additional things. So why is this done? So that I can get a potential here V0. V0 normally we used to take here at the load resistor, but instead what we are trying to do now is we are trying to replicate, and we are trying to make sure that V0 comes and sits here, right? Now, why is this so important? Because this line is actually the feedback line, right? Very important line, because this tries to stabilize your op-amp. So as we have seen previously, having a positive feedback will actually bring in more oscillations, and then the op-amp doesn't be stable. It becomes more unstable. So in order to make sure that we have more stabilized outputs, we have a negative feedback. Now adding to that, it's just like a cherry on the cake. So in order to have or attain the properties of op-amp having very high input impedance, we add a capacitor and a resistor. Okay, so because of which we will be able to attain this high values of Zin. The voltage developed across R1 is actually V1 is equal to Vs minus V0. So Vs is here, okay, the source voltage, and if I have to calculate V1, okay, so that is going to be Vs minus V0. So how much ever resistance or how much ever voltages that are developed here at V0, okay, I'm going to minus that with Vs, because this is the source. I minus it here, I get V1. It is just like I have one unknown and two knowns. So knowns are for me Vs, okay, so and V0 of course we can calculate. So if I want to find out what is V1, so that is going to be the difference between these two. Okay, so see, ultimately we are looking at op-amps which actually work as the difference of the inverting terminal and the non-inverting terminal. The differences between them are amplified. So that's the basic concept that you need to keep in mind. Okay, so moving on, with that derivation, okay, V1 is equal to Vs minus V0. So keep this in mind, please make a note of it. And we can also, mention V0 as actually amplified version of input. Yes or no? So what kind of amplification are we looking into? VOL or open loop or closed loop? OL or CL? What kind of amplification that we are looking into? Open loop, right? So VOL, that is AOL into V1. So V1 here is my input. Okay, just a moment. Yeah, so I am substituting this V0. Okay, I am substituting it as V1. Okay, AOL into V1. So ultimately my output is actually a gain into input. Okay, so or we can even reorganize it, and we can send it to the left hand side and right hand side. So we get it as Vs divided by 1 plus AOL. Now we can also note that, okay, we can note that I1 is equal to V1 by R1. So we have V1 and we have R1. Yes or no? Right? So if I want to calculate the value of I1, then of course I need to know the value of V1 and I need to know the value of R1. How will I get V1? V1 is going to be as discussed previously, right? Vs divided by 1 by AOL. So I'm going to resubstitute this here, okay, since I have the value V1 by R1, okay. So if I make some changes here, okay, if I try to make the inverse of this, okay, I1 is here, so I get Vs here, so I1 by Vs. So if I try to make the reverse of that, okay, so that will actually land up, okay, it will land up with 1 plus AOL into R1. Now this is a very important formula, right, where we need to always probably, this is the most used formula, 1 plus AOL into R1. Okay, now we know that the input resistance, okay, Zin is equal to Vs divided by whatever current. So Vs is nothing but the source voltage, okay, Zin is the input impedance, and so Vs divided by I1, voltage divided by the current, whatever current is getting generated at which point, at I1, not I2. I2 is R2, okay, below the currents that are getting generated at the below resistor, at the bottom resistor. Okay, so ultimately what I have here is Zin is equal to 1 plus AOL into R1. Okay, right, so you can even remember this formula. Zin is equal to 1 plus AOL into R1. Now if we have to, we will just take some values randomly, and we will try to substitute those values in this formula, okay, and we will see what's going to happen. So usually how much is our gain? Is our gain limited, or do we have very high gain? How is it for an op-amp? Can you recall? How is the gain? The gain of an op-amp? Sorry?
Sir, very high. Very high.
Very high, right? So which means, we will just take some random value, okay? We'll take about 200,000, okay, which we have seen most of the times. And we'll take the value of R1 as 47. Okay, so these two we keep in mind, and we just substitute them, okay, and we are getting a very high value. Okay, we are getting about 9.4 into 10 raised to 9. Now actually developing such high resistances is impossible. So usually, as you have seen in your problems, we take up values with mega ohms, right? So 10 raised to 9 is really a huge, extreme high. input impedance. So we have just substituted this value and we found out that it is sufficing for our criteria where my Zin is very large. Okay, so this extremely high input impedance is unrealistic when it is remembered that some stray capacitance is always present. Now always keep in mind whenever there are junctions. Okay, now remember there was a junction between R1 and R2, resistance R1 and R2. So at that point of time, okay, at that point what's going to happen is there is going to be a stray capacitance. So which means at every junction there is going to be a capacitance. Okay, so usually we even refer to it as parasitic capacitance. So we do not need this resistance. Okay, the engineer has not designed it. Okay, like how we have C1, C2, and C3. So we have not designed it, but then it comes up on its own. So these are called stray capacitances. So if the stray capacitance between the circuit input and ground is about 3 picofarads, okay, which is quite possible. So what we do is we try to substitute the value here, okay, 1 by 2 pi 2 pi f, okay, into the stray capacitance. So we are coming up with 53 mega ohms. Is it proper? Can someone verify that for me? And also you can verify this Zin, 200,000 into 47K. Are we getting about 9.4? Yes, are we? Are we getting about 9.4?
Yes, sir, we are.
Yes, sir.
Okay. Now also calculate for this XCS. C is capacitance, S is stray. So impedance with the stray capacitance. Let's see if it's 53 mega.
Yes, sir, it is
53 mega, right? Yeah. So the only extra thing
53
that,
mega.
yeah, that's fine. So we take 53. So the only extra thing that we are doing here is we are multiplying the stray capacitance, right? So it was 1 by 2 pi f, right? So we are just taking the stray capacitance into consideration. Okay, so we are getting about 53. Okay, so which means yeah, since this is much smaller than Zin as calculated above, the effective input impedance Zin voltage follower is normally much lower than determined from this equation. So which means we are not getting these high values, okay, but then we are getting about 53 mega ohms, and this is for the stray capacitance. So to design a high input impedance, so what we do is, we take the same conditions that we had considered previously. For example, at 3 dB, then I'm going to take XC2 is equal to R2 by 10. Remember the same conditions we take, and we proceed with these conditions in mind. If in case the resistance is low, then we bump up the values of capacitance. If the capacitance is high, then we reduce the resistance. So and vice versa. So this is how we actually design. Now, one more important thing that you should really remember is that with the relationship between R1 and R2. So to design a high input impedance capacitor coupled voltage follower, resistors R1 and R2 are first calculated as single resistance which is R1 max. So R1 and R2 is calculated. Now this R1 and R2 is present before the capacitors, before the capacitance, the new capacitance that we have added, right? So R1 max is split into equal two equal resistors R1 and R2. So how do I do that? R1 plus R2 divided by 2, right? To ensure that the feedback voltage remains close to 100% of the output voltage at the lowest operating frequency. So even though we are operating at the lowest frequency, now remember, we have a band of or a range of frequencies. So we have the option to operate at, say, f is equal to, say, for example, 3 kilohertz. If my range is from 3 to 5, then I can go from 3, 3.5, or 4.9 or 5. So at my lowest frequency, which is about 3, for example, I should be able to get about 100% of output voltage at the lowest operating frequency. So it's not mandatory that I should operate at a very high frequency, then only I'm going to get the best result. No, it's not like that. Okay, at the lowest operating frequency, the value of this feedback capacitor, the new capacitor that we have added, is determined keeping this condition. Okay, Xe2 is equal to R2 by 10. So we have seen this. We have seen this previously also. So the same things that we are going to consider, and yeah.
Sir,
Yeah, tell me.
so could you repeat on how a stray capacitance is raised? I mean, how does it come into picture?
Stray capacitance is like between the junctions. Let me go back. Yeah. Now see, this C1 I have designed. Okay. R1 we have put. R2 also we have put. C2 is here. C3 is here. But without my knowledge, there can be some additional capacitors here or resistance here, which I have not done and you have not designed. Right. So these are called, in terms of VLSI, these are called parasitic capacitors and parasitic resistance. Now let us take this junction here, right? R1 and R2. So between, I can have some capacitor here. So this one you will be actually studying when you come to, I guess, 5th semester, your higher semester, where you'll be looking into designing of VLSI circuits. So there, when you get into physical design, okay, so there, when you zoom in to your physical design, then you will understand that there are small resistances and capacitances there formed. Okay, so these are generally termed as parasitic resistances, which we do not want it, but still it comes up. Okay, so it's kind of difficult for us to maintain with all these things, which actually drags down the what to say, the performance of a circuit, right? Yes, have you understood?
Yes, sir.
Yeah, so it's just
Thank
like
you.
this. Yeah, it's just like this. Now let's say I need to walk about a kilometer. Okay, now to walk about a kilometer, probably I will think of, I might feel thirsty, so I carry a water bottle. Okay, probably I need to look at the time, so I'll take my watch. So these are all like additional weight that is adding up to my already existing weight, isn't it? So circuits are also designed in such a way that they perform well at ideal conditions. But when we practically design and when we practically use them, when they come into action, okay, all these capacitors and resistances comes into picture, and they are dragging down the performance. So maybe if I can cover 1 kilometer, just an example I'm giving, if I can cover 1 kilometer in, say, probably 5 minutes, just an example, with all these additional things that I told that I'm going to carry in my backpack, probably instead of 5 minutes, then that might get increased to, say, 8 minutes. So whereby my performance has come down. Similarly, if my outputs, if I'm supposed to get about 5 volts, if I'm getting about 4.5, then there is a loss of about 0.5 volts. So these are called unwanted or not needed. So it's called a stray or parasite. Biologically, what's a parasite? Parasite is something which sits on the living being and tries to take off all the nutrients, right? So the same word is used here, which is parasitic capacitor or parasitic resistance, or we can even call it as stray. Stray is, something we do not want, it's waste. Yes, clear? Can we move forward?
Yes, sir.
Okay.
Yes, sir.
Thank you. So we'll keep these conditions here. Xe2 is equal to R2 by 10, just like how we had seen previously, right? That divide by 10 factor. And yeah, as in the case of voltage follower discussed previously, the output capacitor can be used to set the lower 3 dB, right? This was the thing that I was mentioning about the lower 3 dB. Yeah, lower 3 dB frequency for the high input impedance voltage follower. So we know that, we are going to take Xe3 is equal to RL at F1 and Xe1 is equal to Z in by 10 at F1. So these two conditions we have already seen, but then we are re-implementing it here. Okay. So C3, you can see it is near the load, right? And C1 is actually near the input. The actual input impedance is affected by stray capacitance. Now again, this stray capacitance really drags down the performance, as I mentioned previously. Even if we do not want it, okay, it is going to stay there. And there are ways in which we can minimize it, but there are no ways in which we can nullify it. Okay, so which means we have to just live with it. Okay, so there are a lot of research and development happening, in this area, where how these parasitics together. Okay, when I say parasitics, it means parasitic capacitance and parasitic resistance. So together, these are termed as parasitics. So eliminating these parasitics are kind of challenging, because we have not designed, and it comes without our knowledge, and we get to know about it only when we zoom in or probably simulate and get to know that, oh, instead of 5 I'm getting about 4.5, so something is dragging down. Let me check, let me go back to my circuit, let me see what best I can do. So again, I have to get back to my drawing room and then redesign the circuit and see if I can make some changes to the supply voltage. It's all permutation and combinations that you try to do with the voltages, currents, value of resistance, what kind of wire that you're using to connect from one point to another. Okay. So the capacitance C1 should be very much larger than the likely stray capacitance. So my unwanted capacitance should not be larger than my designed capacitor. Yes or no? Yes or no?
Yes, sir.
So if I have the stray capacitance to be much higher than the capacitor that I am actually designing and putting, so there's no effect, there's no point in having C1. Okay, so which means that gets what to say, it goes for a toss. So which means C1 should be as high as possible compared to the stray capacitance. A reasonable rule of thumb is to select Xe1 is equal to R1 by 10. Yes, we have seen that at F1, okay, at the initial frequency. And we are also considering R1 is equal to R2 and Xe1 is equal to Xe2 and C1 is equal to C2. So generally, as a rule of thumb, why do we say rule of thumb is because, there are a lot of P's and C's which have already happened, permutations and combinations have already happened. And this is the best that we can do. Okay, we can have C1 is equal to C2, R1 is equal to R2, and we make sure that the initial capacitance is about, it's very tiny. Okay, so about 10 times or 10 times lower than R1's value. Okay, the resistor could be included in series with op-amp inverting input terminal in the circuit to equalize, this IB/RB voltage drops. So whenever we have a resistor, there is always going to be a drop, and we have to make sure that these values are mitigated or these losses are mitigated. Okay, so this is not usually necessary when we use an output at the output when we use a coupling capacitor. So whenever we have this coupling capacitor, Okay, it's actually not needed to include another resistor. Remember, we have R2 there. So R2 is actually not needed because I have used a coupling capacitor at the output C3. Okay, but then if really I want to include a resistance, then we need to stick to some rules, right? So what are those rules? It should be equal to R1 and R2. So as I mentioned previously, it should be R1 plus R2 divided by R2. So if in case I want to add another resistor along with my capacitor with the feedback in the feedback line. Okay, so please take note of this last point. It's important. If you have to use a resistor, then it should be equal to R1 plus R2 and should be connected between the inverting input terminal and the junction of C2. So this C2 is actually kept in the feedback line, meaning it should not be in series with C2. So you can actually put it in parallel with C2, but then not in series. If in case you are compelled to use a resistor there, okay, in order to tackle these stray capacitances. Any doubts here? Can I move forward?
Yes, sir.
Okay. So we'll look into one example now, okay, pretty simple example where we are going to use the previously designed circuit. Okay, in a previous problem, we had designed this normal CC voltage follower, okay, but then now we are looking at designing using the same circuit. We want to design a high input impedance, okay. So this was actually used previously and we had got these values. So based on this, we're going to continue the example. So modify the circuit designed in previous example to make a high input impedance voltage follower. Also determine the minimum theoretical input impedance of the circuit. So which means they want us to calculate what is the Z in, okay, the minimum value that it should be, and they also want us to calculate what should be the value of C2 and what should be the value of R2, because I do not have here, right? I do not have here R2, neither I have C2. So keeping this in mind, we will just continue. So from the previous example, okay, we have seen that this is actually taken from the previous example, that R1 plus R2 is equal to R1 max, which is equal to 140 kilo ohms. So if I have to divide it or if I have to average it, okay, so that comes about 70 kilo ohms. So R1 R2 is equal to 140 divided by 2, which is about 70. That's going to be the average for R1 and R2 separately. So I do not have a separate 70 kilo ohms. So as usual, we will be using a 68 kilo ohm resistor. Of course, there's going to be a reduction of 2 kilo ohms. Okay, so that's the thing about this design. We cannot actually put the same value of resistors, but then if you intend to, then probably you can put another 1 kilo ohm or probably 1 kilo ohms in series. Then it becomes about 70 kilo ohms, right? Fine. So now we'll be looking at C3. So C3 is equal to 1 by 2 pi f into R. So 2 pi f is it's operating at frequency 50, and the load resistance, we are going to take the value from here. Okay, so we already have the value here, which is about 3.9. So can someone help me calculate? Are we getting about 0.82 microfarad? .82. Are we getting this value? Please check. Keep in mind the C3 is at the load. Okay, C2 is with this condition that we are taking. Do not get confused and put this formula here and this formula here. Your values will go wrong.
Yes, sir, we are getting 0.816 micro.
Yes, sir,
So
0.816.
Yeah, so we can approximate it to 0.825. So C3 we have got, okay, so C3's value is here. RL anyway we had previously, and C1, yeah, we have to now recalculate. So C2 is 1 by 2 pi f R2 by 10, and just check if, so are we getting this 0.5 microfarad, 2 pi, okay, f is 50, and
Yes, sir. Around
getting
4.68.
4.68, yeah, so yeah, that's fine. So we are getting this 0.5, okay, thank you. So we have this condition, right, where we have C1 is equal to C2. So C1 I keep it as 0.5 and C2 also I keep it as 0.5. So C2 is also done. And now, okay, what we're going to do is we're going to calculate, how much, of course, this R1, R2 also we got it, right? We're using a standard one. So Z minimum, okay, Z minimum is what we have to look into now. So we have the formula C in minimum is equal to 1 plus AOL. Now this also should be minimum value into R1. So 1 plus AOL is taken about 50,000. Now how do I get that value? I get it from the data sheet. Okay, so all those which are needed will be actually given in the question. If not, then we'll provide you the data sheet. So 1 plus 50,000, and please check if it's coming to about 3400 mega ohms.
Yes, sir, it is.
Okay, fine. So the minimum, Z in is going to be about 3400 mega ohms. So this is how, you take your previous circuits, or, whatever circuits are there, you can just convert it from one form to another form. See here, you can see, of course, I have C1, okay, and op-amp is there. Then instead of C2, it is C3 here, RL is there. See, the main thing here is the load resistance is remaining the same. Rest of the values, if you can see, even the coupling, the output coupling capacitor and the load RL, okay, so these are the only two values which are remaining the same. Apart from that, you can see that the value of R1 has changed, okay, because it's just a single resistor here, but then here it's going to be a dual resistor. And you can see that C1 and C2's value also, C1's value has changed. Of course, we do not have C2 here, right, because this is nothing with nothing connected with high input impedance, right? So, this is how, we try to make some changes to circuit. Fine. Now, with regards to the computer analysis, okay, how do we actually develop them? So, as I told you, there are various tools, okay, various software, which is capable of designing circuits. It can be your SPICE or LT SPICE, or many other tools, that you are very much aware of. You can design, in any of the tool, and you can see that, how it is varying. So here you see your input voltage is about 1000, okay, of course in milli, and here it's not very much, the input and output are almost remaining the same, so which means there is no loss at all. Okay, it's just about 6 micro. That is fine, right? So we have C3 about 0.82, then RL is 3.9, then here, the capacitor which is on the feedback line, it's about 0.5 also at C1, right? So the same values, then plus and minus values. Now if we take, the analysis, the frequency analysis, okay, and take the minus 3 dB value, so we have actually designed our system for 50 hertz, but then we are getting about 48.8, okay, 48.8. Now you might ask me, sir, why is it we have we have actually we were very much strict with our design and we designed it, but still we are not able to achieve that frequency. That is because, remember, whatever values that we had calculated, for example, the resistance, instead of 70, we're using the 68 valued resistor. So all this can actually impact. Okay, so you cannot exactly expect that you're going to get a proper 50 hertz design. Okay, so there's going to be a little bit of loss. So, and the stray capacitance that I was talking to you about. So all these can pull down the performance. So that's why whenever you design a system, right, first you come up with what are going to be the specifications. It's just like you're buying a system. You're going to buy a laptop or a desktop computer, and you have in mind that I should have this amount of RAM. I should be able to look into this display size. It can be 15.6 or it can be 14 or it can be 13.3 or 17.5, whatever. So you have certain specifications in mind and you try to mix and match between them, and then you actually come up with the system. So similarly here, when we design circuits, we have some certain values in mind, and keeping all those, we try to design them. And due to these little bit of compromises that we do, and the stray capacitances, and the resistances, so somehow we are not able to achieve this 50 hertz design. We'll be able to maximally reach about 48.8, right? Okay, so still looking into these computer analysis where we try to include a 1 mega ohm. Okay, here we try to include a resistor and we try to see the values. Of course, my input voltage is about 1000, and here there is a drastic change, right? Just because I have included this 1 mega ohm RS, we can see that previously we had about 999, but here there is a significant loss of about 2 millivolt. Or 2 millivolt drop. Okay, so this actually demonstrates that the circuit input impedance is very much larger than 1 mega ohms. So we are just putting here 1 mega ohms, but then our impedance is actually much higher than 1 mega. So if I'm putting this 1 mega, then my output is dragged down. But then if I remove this and normally just send it, okay, we are actually getting a higher value. So now let us look into this figure D. Of course, most of these things that I'm discussing is not going to be there for your exam point of view, but just, if some of you are interested in designing and, mix matching the values of resistances, capacitances, including or increasing or decreasing the values, and, trying to play around with the circuits, then for them, it's going to help. And I encourage everyone to, actually do it. Okay, so now let us come to figure D here, where we are looking at R1, R2, and of course RS is there retained, V1 is also retained, 0.5 is there. I have an op-amp plus VC minus V, and yeah, I have my load and the output coupling capacitor. So what has happened here is I have just removed this capacitor here. Okay, the capacitor here. So it is also called as bootstrapping capacitor. Please note this point. Okay, the capacitor that we actually have with the feedback loop is also called bootstrapped capacitor. So the bootstrap capacitor that gives the circuit a high input impedance is removed, and you can see what is happening to the value of output. Don't you think there's a drastic change? Yes. Yes or no? See this value of output. See this values of output and the previous one. If you compare, what change, what minor change we have done here? We have just removed this capacitor. So just by removing that capacitor, you can see that these values, the output values, have actually, gone too low, right? So there is now about 50% signal voltage drop across 136 kilo ohms source resistance. So not only removing the capacitor, but then we have even decreased the capacitance. So as this capacitance decreases, my output voltage also will decrease. As this increases, okay, my output voltage increase. See here we had 1000K and the value is almost okay. So if I still increase the resistance here, it is going to be as ideal as input voltage, which means as equal as input voltage, right? So you're able to get something, right, as to how the value of resistance can play an important role. What is the value? What is the importance of this bootstrap capacitor, right? Yes or no, students?
Yes, sir.
Yeah. So this shows that the circuit input resistance is equal to the sum of bias resistors R1 and R2. So R1 and R2 are clearly playing a major role here, and we need to have values. Okay, we need to have values which can actually shoot up the values of output. So we need to design in such a way that we get proper outputs. So those conditions should be kept in mind, divided by 10 and all those things. Right. So that's it I have for today's lecture. And, we will be probably discussing the other concepts where we'll be looking into the different configuration, such as how to set up the upper cutoff frequency, and how do we use a single polarity power supply. If remember in my initial classes I had mentioned, if I'm using a plus and minus, then I can use a 15 plus 15 and minus 15. Suppose I want to use just a single, then how much do I need to use? What should be my value at the input? Students, if you can recall.
So 30.
Very good. So this kind of things that we will be discussing in our next session, as to if it's single input, then what should be the levels of voltage and what changes I need to make to the circuit, right? So good, many of you are able to recollect that. Okay, so you should be remembering all these concepts, where that's really going to be helpful as we keep building one by one. Okay, so we have about another 2 topics left out for this module, and yeah, we will be doing it in the upcoming classes. Okay, so any doubts up till this point, students, that we have discussed? Anything that you want to ask? Yeah, is it all fine?
Yes, sir.
Okay.